All right, we're going to start talking about acids and bases today. We're going to start with acid-base theory. There are three primary acid-base theories. We are only going to be dealing a lot with two of them, and really only the one that's kind of in the middle, the Bronsted-Lowry theory. But we're going to start with the simple one. The simple one is the one we've been working with all year. You just didn't know it. I mentioned the name earlier in the year. But every time we've been dealing with an acid or a base so far, we've been thinking about Arrhenius. Okay? But rather than confuse you with the picture here, let's just kind of go on to something else here and show you how Arrhenius works. So the Arrhenius definition, and these are definitions of acids. These are people's names that are given to these definitions because they're the people that came up with it. So Arrhenius, by the way, Arrhenius was a contemporary, meaning he lived about the same time, actually at the same time, as both Bronsted and Lowry. They were all around the same time. They just came up with the different definitions of acids and bases. But Arrhenius is the really simple one. And Arrhenius said that an acid is anything that releases a hydrogen ion, or hydrogen ions, plural, anything that releases a hydrogen ion in water. So far, every time we've talked about acids in here, with the exception of the organic acids, because we did talk about organic acids back in about Unit 4, every physical acid, every non-organic acid we've written a formula for had a hydrogen or more than one hydrogen on the front. And so that hydrogen on the front gets donated to water, and that's what does the work of an acid, at least according to Arrhenius. Now, he also said that a base is anything that releases a hydroxide ion in water. Let's be clear. A hydrogen ion is this, and the hydroxide ion is one of the polyatomic ions that you are supposed to memorize. And we memorized that quite some time ago. There's about 12 of them or so. And you should know that the formula is OH with a negative charge. As we said in the very beginning of this class, this is a very cumulative subject, okay? Everything from Unit 1 on to now is going to come back and, tie in here, all right? Some people might say it's biting you in the behind, but I'm saying it's tying in, all right? So let's talk about the structure of a hydrogen atom. What's a hydrogen atom made of? Nobody knows? Really? A proton. One electron. Okay. Now there are forms of a rare form of hydrogen called deuterium. Deuterium, which has one neutron, and there's an even rarer form of hydrogen that has two neutrons called tritium. And if you remember in Unit 2, we said that's what Dr. Octopus was trying to get to build his fusion reactor. Y'all remember that? Okay. Well, I'm just trying to tie it into popular movies. Okay. But if you didn't see Spider-Man 1, you wouldn't know. Or if you weren't paying attention, maybe. Oh, no, Spider-Man 1. He was in Spider-Man 2. Yep. Anyway, so if we give away this hydrogen ion to someplace else, what do we have left? Huh? A proton. We just got a proton. But somebody said it's a positive, and that is also true. Because what this means is that a proton is a hydrogen ion. They are the same as we are in the context of discussing acid-base chemistry. Okay? If I say proton, you think. If I say hydrogen ion, you think. Got that? No? It's like a cheerleader, you know. Honestly, was it cheer? No? Okay. All right. Now, hydroxide. Well, the hydroxide is just a hydroxide. Okay? It's a water, it's an oxygen atom that joins with a hydrogen atom, and we stick an extra electron on there to make a negative ion, which is OH negative. Okay? That's what an hydroxide is. All right? All right. Now, if we put a hydrogen ion with a hydroxide ion, and we react the two together in a synthesis reaction, what do we get? Water. Okay? And if we have 3 hydrogen ions and 3 hydroxide ions, what do we get?
Water.
3 waters. And that, boys and girls, is Santa Claus' favorite chemical. Huh? Okay. You think? All right. All right. Now, let's talk about yesterday's lab. Okay? In yesterday's lab, we ran a reaction with 2 different acids, and we reacted those 2 different acids with only one kind of base. But they weren't just a pure molecule. They were dissolved in water. So we had hydrochloric acid. Okay, back from about unit 3 or 4, you're supposed to be able to name acids. And so if we have an acid where we have just 2 parts, a hydrogen, in this case a hydrogen, that makes it an acid, and the second part is the anion part of it, then we call this hydrochloric acid. Okay, the hydro prefix is only reserved, specifically reserved for binary acids, acids that have 2 different, just 2 parts, just 2 atoms. Okay, I mean 2 elements, not 2 atoms. All right, binary means 2 elements, not 2 atoms. Right. So hydro goes in the front when we have a binary acid. So this is hydrochloric acid. Now, if we have just pure hydrogen chloride, we can't have an acid. Hydrogen chloride doesn't form an acid until you put it in water or put it in some other liquid. But it's a gas when it's in pure form. All right. So when I put it in water, then it breaks apart. It dissociates. Okay. It ionizes. All right. Remember those terms. Dissociates and ionizes. Okay. Kind of means the same thing in that they break apart in this context. Okay. Remember those complete ionic equations? We had to break stuff up when we put it in water if it forms an aqueous ionic compound. Remember that? Acids kind of behave that way. So if I break this up into separate ions, what do I get? Hydrogen. Do I get anything else? Is that it? There's a chloride? Okay. Is that it? Okay, good. Now it's dissolved in water, so what do we say about those? What else do we write about those? They're aqueous. Okay, good. All right, so that's what we get. So the solution you worked with was not this stuff really. It was really this stuff right here. Okay? When it dissolves in water, it breaks up. It ionizes. It dissociates. Now, let's be clear about what dissociates means. Do you know what associate means? What does that mean? Yeah, you hang around with somebody. You're associating yourself with them, right? Okay? Well, dissociate's the opposite. Okay? So if we dissociate it, we split them apart. All right? Let's see now. The other acid we worked with was acetic acid. Now, acetic acid is a bit different from hydrochloric acid for several reasons, but one thing is it actually dissolves in water before it breaks up, but it still breaks up. So, I want you to write the dissociation part of this equation on the right side. Tell me write down what it's going to dissociate into using this as your guideline. What are we going to break that into? Write it down. Make a prediction. Come on. Have the guts to make a prediction. What's it going to break into? I kind of gave you some hints about it yesterday. Not just kind of gave you some hints, I really gave you some hints. You know? Alright, so what's the first thing I write? H plus, same thing. If it's an acid, it's going to have H plus. Okay? And what's the other part? CH what? Speak up just a little more. CH negative? What about the rest of this stuff here? Okay. What's this stuff called? It's one of the polyatomic ions you're supposed to have memorized. Ah, good. Acetate. Okay? But there's two things I'm missing from this formula. What am I missing from this formula? Aqueous. That's one of the two things. Negative charge. Okay? I can't have a neutral compound. Do you see any charges written over here? No charges written here. So in order for this to be neutral, this positive has to be offset by at least the negative. Does that make sense? You have to have an equal number of positives and negatives. Okay? And this is what we did when we wrote those complete and net ionic equations. We broke things up into separate ions. Alright? Now, we reacted these two acids separately with what? Huh? Not sodium hydroxide, potassium hydroxide. And what was the formula? Grace, what's the formula for potassium hydroxide? KOH. Now, KOH, you might not know this, is a solid when it's in pure form. And we're going to put it in water. And we're going to dissociate it. Okay? Because whenever an ionic compound dissolves in water, it always dissociates. Write the dissociation equation, please. Everybody, write the dissociation equation, please. That's what I feel like. All right. Miranda, tell me what to write. H plus. Is that what you said? Okay. Okay. I suppose that's possible. What did we say this stuff was? Huh? Yesterday we said we're reacting an acid. These are acids with a base. What does this say about a base? Did we release a hydroxide ion? Let's try again. Okay, Bree, tell me what to write. Mm-hmm. Good. Okay. Now, that is, I mean, theoretically, I suppose it's possible, but the most likely outcome is this. The reason being that this is a base, so we're releasing hydroxide ions in water instead of the hydrogen ions in water. Does that make sense, Miranda? Okay. I mean, mathematically, I suppose that's, it's possible. We want to connect the real world theory stuff to the actual stuff we put down on paper. All right. Now, and this is called potassium hydroxide. Okay. Tell you what, since what we did was to react, let's ignore the middle one for the moment, okay? Let's just ignore this one right here in the middle. And let's look at this. Since this stuff, we like to write it like that because it's nice and clean, it's simple, it's actually this stuff right here. And we reacted this stuff right here with the same thing down here, this stuff right here, okay? So what I want you to do is I want you to write all these ions right here, plus all these ions on the left-hand side of an equation. And I want you to figure out what goes on the right-hand side of the equation. Do that now. All these things on the left side of the equation, and then you figure out what's going to happen when you do that on the right-hand side. Okay? Well, they're all aqueous ions. You don't have to put it in water since they're already aqueous. They're already in water. Does that make sense? Yeah. So let's see here. We're going to do H plus Cl negative. So you're helping yourself the most if you try to make predictions for yourself instead of waiting on me to hold your hand across the street. That is to do it for you. Okay, to lead you through. Okay, you want to be the leader of your own mind, not have somebody else become your leader. Okay? All right. What do you think is going to happen on the other side?
The potassium and the chlorine will bond, and then the hydroxide and hydrogen, or the proton will combine to form water.
Okay. So his argument is that we're going to have hydrogen and hydroxide forming water, and the potassium and the chloride is going to form potassium chloride. All right? Well, let's think a minute now. We are in what kind of environment here? Aqueous. Does potassium and chlorine join back together in an aqueous environment? Think about your solubility rules. Okay? Anything, any salt with a group 1 element, like potassium, is going to remain dissolved. If it dissolves and it's an ionic compound, it breaks up. Okay? Chlorine is the same thing. Chlorine's pretty soluble too. All right, there are some exceptions for chlorine, but not much. All right? So these two, while they are there, unless I remove all the water, they're going to stay dissolved. Okay? But you're right about the other part. Okay? So we're going to have the H joining up with the OH. We're going to have the potassium that's going to stay in solution and the chlorine that's going to stay in solution. Okay?
So this should stay discharging?
Yep. Okay, that's how we figured out our complete net ionic equations back in whatever it was, Unit 4 or 5. Okay? What physical state do I assign for water? Liquid. Oops, somebody said aqueous. Does it make sense that water dissolves in water? Okay. All right, I got you, but I appreciate your saying so. That's actually a good thing. I want to make sure we're clear about that. Does it make sense that water dissolves in water? What? Really? I mean, water is just water. It doesn't dissolve in itself. Okay? All right. Water is just water. I mean, you can't dissolve one thing in itself. It just doesn't make sense. All right? At least not the way I want you to think about it. Okay? It might make sense the way you're thinking about it, but I'm trying to change how you think about it a little bit. All right? Okay. So, let's see. You know what? This reminds me of something we did way back in about Unit 4 or 5. What is that? What kind of equation does that look like in Unit 4 or 5 that we did? What was the name of that kind of equation we wrote like that? That ended up looking like this. What? We didn't do Arrhenius acid-base reaction equations of any kind. We did some other kinds of equations. We had, net would have. What is a net ionic equation? What? Takes out the ones that are exactly the same on both sides. Do we have anything that's exactly the same on both sides? Okay, so this can't be the net complete ionic equation. So this has a name, and this is a complete ionic equation. We just put it together differently. Okay? When we were doing it in Unit 4 or 5, okay, we started out with the undissolved stuff. And this time we kind of went ahead and went straight to this. Okay, we just skipped over a step. Does that make sense? And we could write it like this plus this and gives us, KCl, which is what you said, and HOH, and then we could break it all up. We get the same thing. We get to the same place. Does that make sense to everybody? Anybody who doesn't understand needs to let me know now, or forever hold your peace and no complaint about your test grade.
On the test, would we skip it like that, or would we have to do the HCl?
Depends on the question. All right. Any other questions? All right. Can you write the net ionic equation from this? Do that, please. Write the net ionic equation now. Write the net ionic equation now. So in the net ionic equation, we eliminate everything that's exactly the same on both sides, right? So what's left? The proton and the hydroxide. Proton, hydroxide, and the water. After we eliminate all the stuff that's exactly the same on both sides, that's all that's left. And that is the neutralization equation. Really, that's all that's happening from yesterday's lab. Because I had already dissolved the acid.
So we formed water?
Yeah. I already dissolved the acid, and the reason it was an acid, the reason it does the pH, has that low pH, is because this is floating around in there.
So could we have drank that?
This?
No. What we formed?
Yeah. You could have. Nah, you wouldn't want to do that just in case. Okay, not a good practice. But it wouldn't hurt you.
Could you have drank it?
I won't. Okay? Just because I'm being careful. Actually, the KCl in there that's still in the solution, the ions in there, I'm trying to remember. I'm not entirely sure, so don't hold me to this, but I think it has a bit of a, what's the word? An impact on your GI tract. We'll be polite. Not laxative. Okay. I think. Okay. We don't want to do that. All right. Mildly, and probably the solutions we made didn't have enough to make that much difference, but just to be careful, stay away from it. Okay. Now you eat food with potassium in it, bananas. Yeah. You eat food all the time that has chloride ions in it all the time, table salt. Okay. But it's sort of packaged up in a way that doesn't cause that. But if you have a high concentration of, I think, if I remember correctly, I'd have to go look at the MSDS to make sure, huh? That's don't worry about it. Okay. Basically, don't do it. Okay. You have to have potassium and you have to have chloride in your body, but let's don't worry about it too much. All right. So this is our net ionic equation. And anytime we have an Arrhenius acid-base reaction, this is all the stuff that's really happening. This is the real reaction here. This other stuff, just these things right here, they're just sitting around watching. Nope, not that, but this and this and this. Those are our net ionic, spectator ions. They're not really doing anything. Okay? That make sense? Any questions? None? All right then. I'll go on to the next thing.